Professor Fei-Fei Li gave an outstanding talk at the very first WiDS conference in 2015 on the building blocks of computer vision. She shared an overview of the important work that she started with ImageNet back in 2007 and the impact it's had on computer vision as well as on natural language processing. Professor Li's talk is still one of the most popular WiDS videos on our site, and it's still very relevant today as algorithms continue to be improved in order to understand what we see in the world around us. Professor Li is now the co-head of the Stanford Institute for Human-Centered Artificial Intelligence, HI. And after you watch this WiDS talk, you can check out many other excellent talks she's given at HI.
Thank you, and really a great honor to be here. What a special event. Thank you, Margot, for the invitation. So for the next 15, maybe 16 minutes, I'll share with you, it's been a quest for 15 years that for visual intelligence, so we're shifting a little bit from economics and cybersecurity data to actually data you and I see every day. So let's just cut to the chase. We're in a digital information explosion age. And of all forms of data, there is actually one particular form that is dominating our lives. Cisco has estimated by year 2016, data or information in the form of pixels, mostly photos and multimedia data, are going to be more than 85% of the cyberspace. So this type of data will be uploaded, downloaded, shared, trafficked. It's just cluttering our entire cyberspace. So why do we have so much image data or video data? Part of this is due to this explosion of sensors. In the past decade, we see not only an explosion of data in the internet, we see an explosion of sensors that can capture such data, such as our own phones, or sensors in the shape and form of devices and robots, and also in particular markets like healthcare, medicine, this pixel data and imaging data is also exploding. So it is really important, and it's also time for us to understand what's in the contents of these data. And this brings me to this very sobering realization. Pixel data is the dark matters of our internet space, of our information space. So while we get a lot of them, we don't know what's inside. For example, for every 60 seconds, 150 hours of videos are uploaded on the YouTube server. But till today, the bulk of the search of YouTube data is done by metadata, by file names, by usernames, by tags, and so on. We cannot search directly the video content. You cannot type the word or the phrase, a black and white cat taking a bath, and get that video or the bunch of videos out based on just the video content. You have to rely on all the metadata. Self-driving cars, we are in a very, very exciting era for that to be a realism very soon. But still, the sensing mechanism in today's self-driving cars mostly rely on other forms of data. We're still having trouble recognizing a crumbled paper bag on the road, which can be run over, versus a rock of similar size, which should be avoided. Doctors in our medical field, in the past 10 years, radiologists have seen 100 times more data than 10 years ago in terms of imageries. We still don't have good enough algorithms to help them. So the conclusion is that pictures and videos are the dark matters of our digital universe. And this is what I've been working on in the past, in the past years to try to crack this dark matter, to try to shed light to the contents of these dark matters. So why is it so hard? Because you and I see things, cameras take pictures. In fact, camera takes pictures like this by just simply converting lights reflected from the surfaces of the world into an array of numbers. But these numbers do not carry meaning themselves. So it's important to differentiate that seeing is not just taking pictures or forming the imagery. Seeing is really to understand the content of what we see. And this is a hard task. In fact, it took nature 540 million years to do this. 540 million years ago, the first trilobite formed eyes. And it took this long for nature to deliver our human visual system, which is one of the most powerful sensory, perceptual, and cognitive systems in our brain. In fact, it's so important that more than 50% of our brain is involved in visual processing. And nature is one of the greatest economists. It knows how to conserve energy and conserve space. It did not choose to devote this much space for a particular functionality if it's not due to two reasons. One, it's super important. The second is it's super hard. So, so vision begins with the eyes, or artificial vision begins with the cameras, but it truly takes place in the brain. And this is what the field of computer vision is about. Our work is to develop algorithms that can understand the contents of pictures and videos, just like our brain understands our visual world. So to just put us in a common language, I understand not everybody here is in the field of artificial intelligence and computer vision. So what are the basic tasks for computer vision technology or using machine learning techniques? Well, some of the basic tasks are object recognition. These are the building blocks of our visual world. Be it human or robots, we go around and we need to recognize what are the objects. Person identification. This is also key. I don't think I need to motivate this any further. It's just a fundamental functionality that's relevant to all of us. Action recognition, interaction recognition, emotion understanding, intention understanding. As we go deeper and deeper into understanding the visual world, we need to understand all these different components. So for this talk, let's just begin to talk about one of the most important fundamental tasks, which is object recognition. So in the world of machine learning, in the language of machine learning, it is let me just simply put that to develop an algorithm to recognize objects in pictures or videos, you can think about this as showing the machines or the computers a bunch of training images of algorithms as a bunch of training images as examples, as input, and then train a machinery that learns from these training images, and then put an output, an answer. So, for example, if you want to train a cat recognizer or detector, you show the algorithm a bunch of cats. The algorithm learns to what the model of the cat is, and then when it sees a new cat, it outputs the label cat. So that sounds pretty easy, right? Like, especially in the case of a simple object like cat, you can think of it as a collection of shapes and colors, something like this. Blobby body, long tail, pointy ears, and so on. So in fact, this is how we thought about modeling of objects for quite a long time. Of course, we use a mathematical language to describe these geometric shapes, and then use also a mathematical language to configure these shapes. And then we think we have a good cat model. Well, life is not that easy. What about this cat? So Maybe we need a different cat model. Fine. So we have a different configuration of shapes and colors. Well, what about these cats? So things get trickier. In fact, for a long time, this is what we did in machine learning. We used mathematical language to parameterize our object model, and then we just try really, really hard to account for all the variations of the object. And there are so many objects. So you can see this is presented quite a bit of a struggle to us working in the field of computer vision. So about 8 years ago, I actually had a very simple but profound observation that really changed my way of thinking. Nobody tells a young child how to see. I have a 3.5-year-old son. I don't tell him this cat has an elliptical, body or 2 triangular ears and so on. Children just learn by experiences. They learn by seeing lots and lots of examples of this world and also interacting with them in other ways as well. In fact, if you consider a child's eyes as a pair of biological cameras, they take one picture about every 200 milliseconds. So 5 pictures per second. By age 3, they would have taken hundreds of millions of pictures for their training data set. And this is huge. So as I make this observation, I start to think that instead of just focusing on hand-tuning, parameterizing our models, maybe we can also think about data, think about the role data has played in training machine learning algorithms. We probably need a data set for vision tasks that is bigger, that is on par or towards the scale of the kind of data that human has had, bigger than any data set we've ever seen before, both in terms of quantity and quality. So in 2007, my collaborator, Professor Fei-Fei Li at Princeton, and I started this ImageNet project. And our goal is to put together a data set that can help train computer vision algorithms at the scale and the kind of quality that's similar to humans. And luckily, we didn't have to wear a camera in our head and walk around for many, many years like kids. It would have been boring. It would be just office and bedroom. So, so what we did is to use the Amazon Mechanical Turk platform. We downloaded billions and billions of candidate images from Google and other image sources. And then we asked almost 50,000 online workers from Amazon Mechanical Turk. We had to battle the marketplace and trick the workers to work with us to win the competition. Over 167 countries for about 2.5 years. And together, all these workers helped us to clean, sort, and label more than a billion images. And finally, after almost 3 years of hard work, we deliver the ImageNet dataset of 15 million images organized in everyday English vocabulary over 22,000 categories of visual objects and natural scenes. And this became the biggest dataset ever used in the field of computer vision and machine learning to help us rethink about the scale and the scope of the problem of object recognition. And we distributed this entire data set for free on the internet to the entire research and education community. So now we are actually equipped or provided with this wealth of information of data. And as it turned out, this became a driving force for a very important family of algorithm and machine learning algorithm called neural network. Neural network is actually a fairly old concept starting from the 70s and 80s, pioneered by computer scientists like Kunihiko Fukushima, Yann LeCun, Jeff Hinton, and many others. But it turned out the wealth of information provided by ImageNet was a perfect suit for neural network, especially a class called convolutional neural network. For those of you who don't know, who don't work in machine learning, you can think about a convolutional neural network as a loose resemblance of the neural structure in the brain, but I really want to emphasize on the word loose. It's inspired philosophically, but not at the level of all the details. So within a convolutional neural network, the basic operating unit is a neuron-like unit that takes input from other neurons and sends output to others. And then just like the brain, the hundreds and thousands and millions of neurons are organized in layers to process information. So in a standard or typical convolutional neural network that my students and I work with these days, it has about 24 million nodes, 140 million parameters to optimize, and 15 billion connections. And that's just a very typical standard size. So 3 things start to converge at this point. This high capacity model that has been around for a while, but was really starving for data. The big data that ImageNet provided, and also the advance in hardware, especially NVIDIA's GPU computing, helped us to make a huge progress in object recognition. So convolutional neural networks start to perform and deliver the kind of results we've never seen before in object recognition. And here's an example of recognizing cat, of course. Other things like children, teddy bear. Here's another example of an impressive result on small objects in very naturalistic pictures, very cluttered scenes with lots of objects. We can even teach the machine or machine vision algorithm to recognize very fine-grained objects, like 3,000 types of cars organized by make, model, year, manufactured after 1990. I can recognize about 3 of them. But this is 3,000, and we ran this model of 3,000 car classifier over 50 million Google Street View images over 200 American cities. And we learned very interesting things like car prices are highly correlated with household income prices by zip code, or car prices are highly correlated with crime rates in cities. We can even identify which type of cars are highly correlated with crimes. Turned out minivans. You can think about it if you have one. This will be useful next year, that car prices and presidential voting patterns are highly correlated. So really we start to find very interesting things. I started this talk with this overview about pictures and videos. So video is even harder than pictures and harder to harvest as data. We collaborated with Google's YouTube to put together a 1 million video data set and use a deep learning or convolutional neural network algorithm and learn to recognize different video sports in YouTube videos. And now we're really talking about shedding light in the dark matter, right? This is the algorithm, this is the algorithm telling us which type of sports game it is by looking at the pixels, not any of the metadata that is associated with these videos. Let me fast forward a little bit. I'm gonna fast forward this one. This is also, we can train algorithm to recognize social roles of people. So it's not just good enough to say there's person. It's also fun to look at the social roles. I have like 1 more minute, Margot. And And also, so, okay, let me fast forward. I'm gonna skip this one. So now you're gonna ask, is that it? Are we like, is computer solving the vision problem? And we hear that a lot in actually the media hype these days. And I wanna say, no, there's a lot to do. Just putting 1 or 2 labels on an image or on a video is just the beginning. For example, even with children, soon another developmental milestone hits. Children begin to tell stories. Just take this simple picture. A 3-year-old would say,
that's a cat sitting in a bed.
or this one.
Those are people that are going on an airplane. That's a big airplane.
So you can see children starting to tell you the overall gist and the holistic story of the scene, not just say airplane, person. So we are now taking to the next step of combining natural language data with vision data and training deep learning algorithm that combines the information of snippets of the visual scene with snippets of the natural language, and then start to learn to tell a story when it sees a new picture. And here is a very preliminary
a large airplane sitting on top
result.
of an airport runway.
This is generated by a computer. Seeing this picture for the first time, it's not as cute as that 3-year-old, but it is telling the story. Here's more results.
Standing next to an elephant.
Let me.
A cat lying on a bed in a blanket.
We're starting to make mistakes because the internet has too many cats, and we train with too many cats, and our algorithm is too cat happy, and.
A young boy is holding a baseball bat.
Not enough context. One last thing.
A man riding a horse down the street next to a building.
Nothing is totally wrong in this description, but we could do better. So in conclusion, there's a lot more to be done in vision. And just looking at this picture, this is a picture of my son, and looking at how much we can see in this picture beyond objects, beyond the person with the cake. Think about his emotion. Think about the 3D layout of the scene. Think about what we can do. I'm just personally very excited. This is really the beginning of a very exciting generation for big data, marrying computer vision and machine learning. Thank you.
Fantastic. Thank you.